So I'm Jack, and this is joint work with Daniel Greer, who's my advisor at UC San Diego. And the title of our talk is Quantum Threshold is Powerful. So perhaps you think this has something to do with the threshold theorem and error correction. It does not. This is a talk about circuit complexity. So sorry to disappoint any error correction fans. Okay, so let's see. Yeah, so the motivating question for this work is, what is the power of large multi-qubit gates in quantum circuits? And so the setting we'll be working in is where our circuits consist of arbitrary 1 and 2 qubit gates and then some restricted class of multi-qubit gates. And so on the left here, you can see this gate computes the parity of a bit string in superposition. And to refine this question a little bit more, we add the caveat that the circuits we consider, in addition to having this restricted gate set, are also of constant depth, meaning the depth does not scale with the input size. And there are a few good reasons for thinking about constant depth circuits, one of which is that we know that they're quite powerful. So in particular, we have separations where a constant quantum circuit can solve a search problem that's sort of an analogous constant depth classical circuit provably cannot solve. And these separations are nice because they don't rely on any sort of unproven assumption. Moreover, that a algorithm can't sample exactly from the output distribution of a constant depth quantum circuit unless the polynomial hierarchy collapses. Moreover, in the classical setting, we have sort of a nice wealth of knowledge of what constant depth circuits are capable of, at least compared to sort of the lack of results we have quantumly. And so, throughout this talk, we're going to be asking about which sort of classical circuit results we can perhaps port over to the quantum setting, or at least investigate what happens when is. So in particular, we're going to be mostly interested in decision problems today. So on the left here, you can see we have some Boolean circuit that takes as input n bits and then produces a single bit of output. And then on the right here, you're probably familiar with how quantum circuits compute Boolean functions. So for example, parity is one such function we might hope to compute. And there's a slight asterisk here because this is going to end up not being exactly an apples-to-apples comparison between these two sort of models, but I'll touch on that later. So like I said about porting classical results over to this quantum setting, let's suppose we have some statement of the form C1 is strictly contained in C2, where these are classical circuit classes. We might be interested in asking sort of the analogous quantum question about quantum versions of these classes, say QC1 and QC2. So when is it the case that strict inclusion also carries over to the quantum setting? So sort of a first example of this is sort of a landmark result in classical circuit complexity, which is that AC0 is strictly contained in AC02. And so AC0 is defined as the set of decision problems decidable by constant depth classical circuits, which consist of AND gates of unbounded fan-in, let's say. And with the 2, we also get unbounded fan-in parity gates for free. And so, first proved by Itai, first Sachs and Sipser, and then later by Haustad, that AC0 cannot compute the parity function. And sort of for trivial reasons, AC02 can compute the parity function because a single parity gate is in an AC02 circuit. And so the method by which this can be proven is this famous technique of random restrictions, where we sort of sample some inputs from a distribution randomly, and then with high probability, this sort of like simplifies our AC0 circuit. I won't get into this, but it's a very nice classical technique. And so now we want to ask the question: does a similar result hold for a quantum analog of AC0 and a quantum analog of AC02? And so, unfortunately, this question has been, been very hard to answer for at least 20 years since these sort of analogous quantum models have been defined. So there's a number of papers here that sort of set out to answer this question, but fall short and are perhaps only able to prove particle results. And so this is not going to be the focus of this talk. Instead, we're going to ask some different questions. To reiterate, this question of QAC0 versus QAC02, so sort of unconditional lower bounds on these constant depth circuit models are sort of notoriously difficult because like I said, constant depth quantum circuits can do things that are sort of very different from what's possible with constant depth circuits in the classical setting. And so this sort of prevents us from taking any of the lower bound techniques, these classical ones, and just sort of naively porting them over to the quantum setting. And on the second bullet point here, there's a sort of interesting relationship between what's called fan-out and parity, which I'll talk about in a little bit. Yeah, I mentioned classical techniques sort of don't really have a straightforward way to be made quantum. And so this sort of motivates the real question behind this work, which is, okay, if we can't prove unconditional lower bounds, then we should ask which other multi-qubit gates are as powerful as this parity gate. And that leads to the title of our talk, which is that these so-called quantum threshold gates are examples of such gates. Okay, so there was this red asterisk earlier when I was sort of laying out the quantum and classical models that we're thinking about. And so both classes consist of some restricted set of gates, and we can define quantum analogs of these gates. But one thing that we can't exactly do quantumly that is sort of assumed in our classical circuit models is the ability to fan out a single bit of information. And so what this looks like is a single gate evaluates some function on 2 bits and then fans the results out sort of an unbounded number of times. This is sort of assumed in the definitions of all these classical circuit classes, but you might notice that this isn't exactly a reversible operation. And so there isn't really a way for us to do this with 1 and 2 qubit gates, for instance. And so we need to define some sort of unitary that does this. And so you can see here we have some B bits for the first qubit here, and then we just XOR it with all of the other bits to which we're applying this fan-out gate. And so you can sort of naively decompose this as like a depth n circuit of C-naught gates. But somewhat turns out that if you add this gate to your gate set, in addition to arbitrary 1 and 2 qubit gates, this fan-out gate, then you immediately gain the ability to compute parity. And so this was first observed by Moore in 1999, and the proof is rather simple. You just conjugate this fan-out gate by Hadamard's on every single qubit, and the resulting gate is exactly this unitary which computes parity. But this is sort of like uniquely quantum and quite weird because, like I said, in these classical circuit models, we assume that this fan-out ability is just a given, but it does not allow for us to compute parity classically. So something a bit strange is going on here. So let's return to our story about which classical results can sort of be ported over to the quantum setting. And so another example is that AC02 is strictly contained in TC0. So let me define what this is. We just saw what AC02 was. TC0 is what happens if we take, say, AC0 and allow for it to also have majority gates anywhere in the circuit. And 0 again means constant depth. Oops. And so, yeah, it was first proven by Razborov and Smolensky in 1987 using the so-called polynomial method that even with mod 2 gates, there are still functions you can't compute. In particular, you can't compute this majority function. Okay, so now we may naively ask again, can QAC02 be placed strictly inside of QTC0? And the answer is no. In fact, we can say something quite strange, which is that TC0 is actually contained inside of QAC02, meaning that if you have parity gates, no matter if you have large AND gates or not, so QNC02 here is when we have parity gates and arbitrary 1 and 2 qubit gates, we can compute majority, meaning that we can simulate these QTC0 circuits. And this was first proven by Hoare and Spelek in a paper titled Quantum Fan-Out is Powerful. And so that is sort of where our title comes from. And at least prior to our work, it was not known that QTC0 contains QAC0 too. So it was not known if this containment was strict or inequality. And so, yeah, so on the left here, we have sort of the inclusion lattice. All of the solid lines are strict inclusions, and the dotted lines are inclusions that are not known to be strict. And so sort of the first interesting difference between the quantum picture and the classical picture is that classically, we sort of have this innocuous class, NC02, very much near the bottom. In particular, this class can't compute and. But in the quantum picture, it's essentially at the top. It's essentially the most powerful of all of these constant quantum circuit classes we've discussed so far. And sort of the second nuance here is that TC0 is sort of the classical circuit model that can sort of do everything that all of the other ones we've talked about can. But on the right, it's sort of it's unknown whether or not, or at least it was unknown whether or not this class is as powerful as the most powerful classes we've talked about so far. But that leads to our main result, which is that quantum QTC0 can indeed compute this parity function, and therefore we can say that QTC0 contains QNC0 too. And there's one caveat to our result, which is that while all of the Boolean functions in the class on the left can be computed right, there's some approximation error inherent in our construction. So say with 1 over n error. And this is also the same as the constructions of Hoare and Spelek, but this was later made exact by Takahashi and Tani 6 years later. So maybe someone will do the same for this result. One sort of bonus to cancel out the caveats is that our construction sort of applies to a generalization of majority that sort of crops up in an interesting way. And in particular, this generalization is sort of useless classically. It really doesn't seem to be useful for understanding classical circuits. But quantumly, it seems like it is sort of giving us some insight into why this is true, into the structure, at least, of these quantum classes. Okay, so if you've studied some classical circuit complexity, you might ask, why isn't this result trivial? Like, we have TC0 far above NC02 here, the sort of classical analogs of the classes in our result. And how you can see that TC0 contains NC02, in other words, how you can see that a classical threshold circuit can compute sort of via the following very simple circuit. So we can sort of exactly compute each of these Hamming weights, just check whether the input has Hamming weight 1, 3, and so on for every possible odd Hamming weight, and then take an OR over all of these, and the result will be the parity of the string that we had as input. And so you might ask, okay, why can't we do this quantumly and get the theorem that we just saw? That there is sort of some fan-outs inherent in this construction. So in order to do something like this, a sufficiently shallow computation of parity with TC0, you need a large fan-out. You need a lot of wires. And there are theorems proving this. And remember, quantumly, we don't have this fan-outs sort of included in our gate set for. So, okay, for the rest of the talk, I'm going to sketch some idea of how to prove this, how to compute fan-out or parity just using majority gates and 1 and 2 qubit gates. And so this will go along the lines of a result proven by Rosenthal in 2020, where first we show that there's a state preparation task which suffices to compute fan-out, and then we'll give a circuit which performs exactly this state preparation task. And so the state preparation task in question is the so-called cat state observed by Moore in the paper where many of these classes are defined. So in particular, if you can implement a circuit U, which takes all zeros as input and leaves you with this sort of maximally entangled cat state, then using U dagger, and OR gates, you can compute parity. I won't get into how this works, but it's a very nice and simple circuit. So if you're curious, talk to me or check it out in Moore's paper. But this is a very strict, but it turns out that you can sort of loosen the type of state that you need to prepare in order to still be able to compute parity in this way. And so what I mean by that is it actually suffices to prepare a state that only looks like a cat state on the first n qubits. So here you see we have this psi 0 and psi 1 hanging off the end of our cat state, where these are some arbitrary states. And it turns out that if you can prepare this state, this is sufficient to compute parity, sort of in this Moore style. And this was observed by Rosenthal in the same paper I just mentioned, and he terms these nekomata states, which is quite a fun term. I think it's like a Japanese folklore term for a two-tailed cat spirit. Anyway, yeah, and further, if you can compute one of these states, so some state that has high fidelity with the state of this form, then you can also approximately compute parity with essentially the same approximation guarantee as the state preparation task. Right. Yeah, so I'll just mention how Rosenthal, what his results are, and sort of the outline of how they're proved, because our proof is along much the same lines. So he proves that there are constant depth QAC0 circuits that are able to prepare one of these approximate nekomata states up to inverse exponential approximation error. But the sort of trade-off is that the resulting circuit is of exponential size. And so the key idea in this proof is to prepare many what I'll call bad but not horrible cat states, and then somehow boost the entanglement that they have in constant depth in order to end up with one of these nekomata states. And I guess what I mean by bad but not horrible cat states is that each of these states has low fidelity with the cat state, so it's sort of a poor approximation in a fidelity sense, but it has a measurement distribution with sort of the right properties. And so what I mean by that is with the cat state, if you were to measure it, you would see all zeros or all ones, both exactly half of the time. But with one of these bad but not horrible cat states, all I'm hoping for is that we'll see 0 and 1 sort of as the unique peaks of measurement outcomes if we were to measure it, with everything else happening with negligible probability. Okay, so yeah, let's get to how we'll construct one of these nekomatas. So this circuit construction looks like a grid of qubits, an m by n grid of qubits, where this first column here is going to be sort of the cat-like part of the nekomata state here, which measures all zeros or all ones with probability about a half. And then this grid over here is going to be sort of the junk, the psi 0 and psi 1. Right. And what we're going to do is we're going to construct one of these bad cat states on each of these ancilla columns that has most of its mass on all 0 and all 1, perhaps in some sort of uneven way. And then what we're going to do is m, the number of columns in this ancilla block, to be large enough such that the probability that all of them measure this all ones outcome happens with probability about a half. And what this means is that if one of them doesn't result in a measurement that's all 1, well, the next most likely thing for it to be is to be all zeros. And this is sort of a desirable thing for this block to have, because if all of these are all 1, and then we apply an AND gate with the output being XORed into this target column, then every target column, each of these target qubits will be 1 if each of these all measured all ones. However, in the case where one of them is not all ones, then the most likely thing for it to be is all zeros, which means that every single qubit in one of these columns on the right here will be all zeros, and none of these AND gates will do anything, leaving all of these qubits as all zeros. And I have that illustrated here. Okay, if one of them is all zeros, the AND gates don't do anything, all zeros. Okay, now before I get into how we sort of get to these bad but not horrible cat states, I'm going to introduce a piece of machinery that we call a parity-restricted gate. And so what this is a gate that acts by taking some basis state x and adding a phase depending on whether or not it's a member in some set S. And in particular, S we're going to call a parity-restricted set if every member of S has the same parity. So they're either all even or all odd, but it doesn't matter which. Um, and yeah, you'll maybe recall from the construction here that if you can compute some threshold function, like say majority, then you can pretty easily compute the Boolean function that checks if the weight of the input is exactly some value. So for majority, that would be over 2. And the result would be the same Hamming weight, and in particular, they'd all have the same parity. So this is some sort of generalization of these threshold and exact. Right. And it turns out that the sort of only relevant property of these sets S, or the only property we need for them to have, is to be sufficiently large, so to be like sufficiently dense in the of the Boolean cube that they occupy, and for them to be parity restricted. Okay, so this is the circuit that constructs one of these bad but not horrible approximation states. And so what you can see here is we've defined this state psi s, which is exactly what you get when you conjugate this parity restricted gate by Hadamard's and apply to all zeros. And what we're going to do is we're just going to reflect about psi s on the all ones input. And it turns out that when you do this, if you work out the math here, the probability that the resulting state measures all zeros is this quantity sort of only depending on ds, the density of the set S. And the probability that we measure all ones is something like 1 minus some polynomial in this density ds. And so this sort of like exactly corresponds to what I showed you earlier, and ds is chosen appropriately. Okay, and so just to recap how this construction works, we're going to start with our grid with the target qubits on the left here and the ancilla on the right. And it turns out that if we pick the number of columns to be approximately 1 over some polynomial in the density, then it turns out that every column will be all ones with probability very close to a half. And the probability that some column is all zeros is also very close to a half. And the approximation here is some function of the density. In particular, it's the some polynomial density. What this means is that if you have majority gates, then like I mentioned, you can sort of recover these exact n over 2 gates. And this will leave you with some parity restricted sets. But I didn't say anything about what its density was earlier. Yeah, you just do sort of a Stirling estimate. The resulting density will be about 1 over root n. And what this means is that, yeah, these probabilities here are going to be roughly like a half minus 1 over root n. The resulting state is going to have high fidelity with some Nekomata state. In particular, it's going to have fidelity like 1 minus. Right, and so this sort of leads to our theorem statement, which is that if you have US and AND gates at your disposal, then you can construct a circuit of size polynomial in n and 1 over the density of this set, which computes parity, actually, which prepares one of these approximate Nekomata with approximation error that's like roughly the density. And as a result, you can use this from Moore's reduction to compute parity and fan out and all the other things you could hope to compute. Okay, and in particular, this gives you polynomial size quantum threshold circuits for parity and the circuit inclusion shown to the left here. The complexity class inclusion shown to the left here. And then I guess another thing I'll note, I mentioned this result of Rosenthal earlier, which is an exponential size QAC0 circuit that prepares one of these states or computes parity. And it turns out that you can sort of just view his construction in the same language that we've used here, where the parity restricted set he's considering exactly corresponds to what the AND gate computes, which is it just picks out this all one string. And so singletons are, of course, parity restricted sets. So you can sort of view our construction as a direct generalization of what Rosenthal did. And so I guess I'll just end with a few open questions. Yeah, to the right here, we sort of have the updated inclusion lattice of these constant depth classes. In particular, now we know that QTC0 is, in fact, at least as powerful as any of the classes below. So I mentioned throughout that there's some error inherent in our construction. In particular, this shows up with these sort of bad but not horrible cat states. I mentioned that there's some negligible probability that they measure something that's not all zeros or all ones. And so it's sort of an interesting question to ask whether or not this can be taken to zero. Can this error be removed entirely? Second is sort of one of the big open glaring questions from quantum circuit complexity, which is whether or not this class QAC0 can compute parity or not. Yeah, perhaps it would be useful to look at these other functions now, which we know suffice to compute parity. Perhaps it's easier to give lower bounds, QAC0 lower bounds against those rather than parity directly. And third is the question of which threshold functions can be computed by QAC0. So our construction uses threshold functions to compute parity, but it's similarly well motivated to ask which threshold functions you can compute with, say, just AND gates. And then finally is sort of a more open-ended question, which is, yes, we introduced this idea of parity-restricted gates, but can we get a more complete characterization of which gates suffice in constant depth to compute parity? So yeah, that's it.
Questions?
So great talk, and I had written some few questions, so they are quite long, so I had to write them. So my first question would be like, can we identify necessary and sufficient conditions on a multi-qubit gate G such that the constant depth quantum circuits with access to G and arbitrary single qubits can compute fan-out with high fidelity?
Yeah. So that's sort of getting toward this last question I have here. Like, from this work, we at least know that sufficiently large parity-restricted gates suffice. But I would expect for it also to be the case that you can define some notion of parity restrictedness, sort of mod 3 or mod any other prime. This is something we haven't really explored, but I imagine the proof would go much the same way. Sort of if you work over like p-dimensional qubits, then you can compute this mod p function in a similar way.
Yeah, and one more question from my side. So is it possible to construct polynomial size constant depth circuits with only generalized Toffoli gates that can compute fan-out operation?
Yeah, this is exactly this question here. Yeah, the class you described, polynomial size circuits with generalized Toffoli gates.
And one more question from my side, like, are there any other alternatives for multi-qubit gates which are more powerful than fan-out in constant depth?
Yeah, as far as I know, the answer is no. I mean, I suppose you could define gates based on some very hard to compute Boolean functions, but it's like unclear if this is maybe physically well motivated or not. I don't know. Yeah.
Sure. So that's all.